the implementation. Yeah. We need 4 parameters. The first parameter, the number of disks. Then 3 integer numbers, we just use 1, 2, 3. Okay, peg 1, peg 2, peg 3. Yeah, 3 peg numbers. Yeah. The peg numbers we arrange in a special order. Yeah. The first peg number, that's the beginning peg. Then the second peg number, the destination. Destination 1. The third peg, temporary peg. Yeah. Because when we do recursion, yeah, the reason we, make rules like this, because when we call the function recursively, we need to specify the rows of different pegs clearly. Yeah, so that's the reason. Yeah. Then, the first time when we call the function recursively, the disk number reduced by 1, and you need to, change the rows of the 3 pegs. The beginning peg, same. Yeah. Then, your destination should be the temporary peg as the destination. Then, your destination peg, you use it as the temporary one. All right. Then, the gap part. Yeah. So this, you print out the message. This printout message, just a simulation. Yeah. So you use this statement, simulation of the move. Okay. So one move. That tells us it's one move in simulation. Right. All right. After that, you do another recursive function call. Yeah. Also, solution n-1 solution, and you need to change the rows of your 3 pegs. Then the temporary, this temporary one you use as the beginning peg. Destination, that's the real destination peg, but the from peg you use as the temporary. Yeah, so you arrange in that way. Yeah. Here you can see, even if when you do recursive function call, you really need to, work on the parameters carefully. Yeah. The meaning of the parameters. Yeah. Carefully, treat the, the meaning of different parameters. Yeah. All right. So we complete the whole solution. Yeah. Here you can see, after we solve this problem, this n-disk problem, think about this n-disk problem. Pretty hard, right? N-disk problem. But our code, implementation code, so short. Just a few lines. Just a few lines, we can solve such a, pretty hard problem. Now you can see the power of recursion. Yeah. You can imagine without using recursion, how can you solve this problem? Yeah. Theoretically, you can solve, but realistically, I believe nobody can do it. Realistically, right? Yeah. Yeah. Theoretically, yeah, people can do it. Yeah. Yeah. Especially when the n number is large, how can you do it? Yeah. So now you can appreciate why recursive algorithm is so useful, because its power is so big. Yeah. We want to use its power. We are willing to sacrifice the resource. We need to use a lot of resource. Yeah. So here you can see, in order to use its power, yeah, big power, we are willing to use more resource, pay more resource to get it. Yeah. So that's the whole idea of the basic understanding of recursive algorithms. Yeah. All right. Next, the last topic of part A, 8.3. Solve first order recurrence relations. Yeah. Here there is one question left. Yeah. The last question. How many disk moves? We need to know. In our 3-disk problem, we know we need to make 7 moves. Right? Yeah. So when n equals 3, we need 7 moves. Okay? Yeah. Now, for the general n disks, the problem, we want to know how many moves. What's that formula? Number of moves, that formula. We want to know that. Yeah. To get that answer, we need to solve first order recurrence relations. Yeah. All right, so let me show you the equation first. Yeah. We need to derive that recurrence relation for the number of moves. Yeah. All right, yeah, the question. Yeah. First, this is the recurrence relation for the number of the C function. The C function, we count. We count the number of moves. All right? Yeah. When n equals 1, the base condition, we just need one base condition. C of 1 equals 1. One move. Yeah. After that, the general formula. Yeah. All right. When we need to solve n disk size problem, how many moves? Yeah. We use the function capital C of n representing the number of moves. Let us recall. How do we get the C of n number? Yeah. Remember 3 steps. Step 1, we apply P of n minus 1. So P of n minus 1, we need C of n minus 1, this many moves. Yeah. After that, we move the bottom disk, 1 move. Okay, that's this plus 1, 1 move. Yeah. After that, another P of n minus 1, that's why we double it. Okay, because we apply P of n minus 1 twice, so this counting function, capital C counting function, we should use multiply by 2. Yeah. So this is the recurrence relation. Yeah. All right. Then, so this equation we called the first order recurrence relation. Okay. Yeah. So first order recurrence relation, because so look, the right hand side you can see we only use C of n minus 1. Yeah. One function call of one of the smaller size number, the first term. Yeah. Or you can say this, the difference is 1. The size number difference is 1. Okay? Yeah. Similarly, so if I may give you a size 2, order 2 case, or we call a second order case. If I write C of m equals 3 times C of m minus 1 plus 2 times C of m minus 2, yeah. Although I can plus some number, but this number does not change the size. Okay? All right. So here you can see the difference, n size and the smallest size number here, n minus 2, the difference is 2, then we call it second order. Okay? Second order. All right? Second order, much harder than first order, so we leave it to part D. We solve second order. Yeah. Here, let's solve the easiest case, first order recurrence relation. Yeah. All right. Yeah. To solve it, yeah, here we still use our problem-solving strategy. Okay, so here, I keep using a few simple strategies again and again, but very effective. Yeah, very effective. Yeah. All right, so here, let's do this. Yeah. Let's recall our old strategy. Yeah. When we solve a problem, we want to simplify the problem first, right? Yeah, we want to solve a simplified version. So there is a strategy. Yeah. So here, actually, this strategy is slightly different from our simpler versions. Yeah, simpler cases. Yeah, we did simpler cases before, right? So here, this is slightly different from that strategy. Okay, the simpler cases still the same problem, but the cases are simpler, right? Yeah. Here, actually, we modify the problem. The problem is slightly different. We modify the problem. We change the problem. So this is another commonly used strategy in problem solving. But this time, we modify the problem, make it simpler, and then we solve it. Yeah? Because the difference is small, we can fix the gap later. Yeah, that strategy. Okay? All right. How do we modify the problem to make it easier? Here you can see this +1 is quite annoying. That +1, you just add one number, but that one number make the problem harder to solve. Okay? All right. So first, we want to simplify the problem. We drop this +1, make it simpler. Okay? Yeah. So we modify. Modify the original problem. Let us consider C of n equals 2 times C of n minus 1. Just drop one. Okay? Do you feel this is much easier to solve by dropping that +1? Yeah. Yeah, very easy. Why? Because the difference between two consecutive solutions, the counting number just multiplication by 2. That's the difference. Okay? All right. Then, if you want to move to, because this C of n minus 1, can you use 2 times C of n minus 2 to replace it? Right? Recursion, another recursion. C of n minus 1, 2 times C of its previous size, a minus 2. Yeah. All right? Then, you simplify, so you get 2 squared times C of n minus 2. Right? Yeah. Then, can you do another recursion on the C of n minus 2? Another round recursion call, right? Yeah. So you can write 2 squared times another 2 times C of n minus 3, right? By recursive formula, okay? Then you get a 2 cubed times C of n minus 3. That should be enough, right? Yeah. That should be enough. Yeah. From, these representations here, can you get, because we need to get to the last step. Last step, C part should be C of 1, right? C part should be C of 1. No? That's our base case. Then, the power function, not the 2 to some exponent. Can you tell me what is that appropriate exponent number for 2? We know, because we multiply 2 many, many times. At the end, what is the suitable number we should put at the exponent of the power of 2 number? Can you figure that out? Think about that. Some number, appropriate number. Yeah. Can you get idea? The appropriate number? Okay? dot 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 here. Yeah. Remember, when we have dot dot, we get lost, right? It's hard to keep track of data. In order to keep track of data, what method do we use before? Let's recall. We have some special method, right? Help us keep track of the data. Find some invariance, right? Apply the invariance method. Can you discover some invariance property here? Invariance property here. Okay? All right, so here, I'll show you. The first two here, can we treat as 2 to the first, exponent number 1? Okay? All right. Exponent number 1, the problem size n minus 1. Can we add them together? 1 plus the problem size n minus 1. We get n, right? Yeah. And here, exponent number is 2. Then we add the problem size number n minus 2, also n, right? That's a fixed number, right? That's the n. That's invariance. Okay? Now we apply invariance. This number here, invariance, but 1 plus that number should be n, right? Can we say it should be, oh, sorry. Yeah. Can we say it should n minus 1, right? Oh, sorry. Yeah. It should be 2 to the m minus 1, C1, right? Yeah. Okay? Yeah. All right. C of 1 given, so it is 2 to the n minus 1. We find a solution in this way. Yeah. All right. Yeah. Here, you can see that invariance idea. Very useful. Okay? Very useful. Yeah. 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 So we practiced several times. Okay? Yeah. I hope after you finish this class, you should get pretty good training on that invariance method. Okay? Yeah. We still have a few more chances to apply that invariance method. Yeah. All right. But this is a modified problem, right? It's not an original problem. After we find the solution, now we need to go back to the original problem. Yeah? So because, our goal, we need to solve the original problem. Yeah. All right. So let's go back to the original problem. The next question. This time we add that 1 back. The next question is, how do we connect the original problem and our modified problem? The difference is small. Can you do conversion from one to the other? Yeah. Conversion. Yeah. So here we want to take care of this plus 1 part. Take care of that 1 plus 1 part. Okay? All right. Yeah. Here, let me apply some special technique to show you how do we bridge the gap. How do we do the conversion from this current version to our previous modified version. Okay, all right. The little trick is like this. We add 1 both sides. This inequality, can we add 1? C of n plus 1 equals 2 times C of n minus 1. Plus 1, is it plus 2? Plus 1 plus another 1, plus 2. Can we factor that 2 out? 2 times C of n minus 1 plus 1. Right? Yeah. After that, now, we have a newer version. Look at that. Left-hand side, C of n plus 1. Right-hand side, inside parentheses, C of n minus 1 plus 1. Do they have similar structure? They have similar structure, right? If they have similar structure, can we use a new function to represent the structure? New function, let me call D function. D of n equals this C of n plus 1 function, D function. Okay? D function equals, inside parentheses, can we use our new D function? It should be D of n minus 1, right? Okay? So D function, D of n equals 2 times D of n minus 1. Okay? Do you see this D function just, it takes the same form as our modified version? Because plus 1 is gone. In this D version recursive formula, plus 1 is gone, right? Plus 1 is gone. Okay? All right. But this D function, after we introduce this D function, we need to fix that base case. D of 1 is the base case, right? What's D of 1? D of 1 is C of 1 plus 1. C of 1 is 1, so D of 1 is 2. It's 2, not a 1. Okay? It's 2. Yeah. All right. Now, when we solve this one, we can use our previous solution. Previous solution, it should be 2 to the n minus 1 times D of 1, right? 2 to the n minus 1 times D of 1. D of 1, we know it's 2. Okay? Yeah. Then we multiply 2 for the D of 1. We get 2 to the n. Okay? So D of 1 function is 2 to the n. Then we can go back to C function, yeah, because the C function, C of n equals D of n minus 1. That is 2 to the n minus 1, right? Because D of n is 2 to the n. 2 to the n minus 1. Yeah, let me write the final formula. The final formula, C of n equals 2 to the n minus 1. The final formula. Okay? All right. Then you can verify it. Verification. When n equals 3, 2 to the third minus 1, is this 7? Right? Yeah. So you plug in 3, 7. Yeah. All right. After that, then, after we get this formula, now you can see if we need to solve a 10-disk problem, n equals 10, then you plug in n equals 10 here, 2 to the 10 minus 1. You need this many moves, 1023. You need this many moves. Okay? Yeah. So here, we derive the formula. Try to understand the details. How do I derive this formula? Okay? Yeah. Here you can see we go back to the problem solving. Yeah. Yeah. But this time we modify. Yeah. We are allowed to modify the original problem to make it simpler. Okay? Yeah. Then after you find the solution for the simplified version, then you need to go back to the original version, but you need to fix that gap part. You need to do some work fixing the gap. Okay? Yeah. Yeah. So then you find the final solution. Yeah. Yeah. All right? Yeah. So that's the, point, main point. Yeah. All right. Yeah. So we finish part A of module 3. Yeah. Next, let's move to part B. Yeah. Part B. Yeah, because for next class, we need to complete both part B and part C. Yeah. So I hope I can finish half of the part B today, then the remaining half next class, then part C, also next class. Yeah. All right. Let me get out of the part A first. All right. Move to here, part B. Okay, all right. Change my pen color. All right. The topic, variable size reduction. In part A, we learned one size reduction, reduce size by 1. Okay? But this part will allow to reduce more size numbers. Yeah, so variable size reduction. Yeah. Sometimes smaller, sometimes larger. So variable size reduction. Yeah. B.1, reduce problem size by half. Yeah. That's, relatively big reduction. Size by half. Size number by half. Okay, all right. Look at the question here. Count the binary digits. Yeah. All right. Yeah. The problem, pretty easy. Yeah. Given a positive decimal integer n, yeah. But the original form decimal system, we use decimal system. Yeah. But we want to look at its binary representation. In the binary representation, we want to find the binary digits, or we call it bits, the number of bits. Yeah. Yeah. If you do the binary conversion, how many bits do you need to use? That's the question. You need to write the number of bits in terms of this n number formula. Okay? Yeah. That's the question we need to solve. Yeah. All right. Yeah. So here, let's do analysis. When we start, we want to review the binary representation, the structure, binary representation structure. Yeah. We know when we write n, the decimal representation n, in the binary system, we need to change our base. Yeah. Numeral base, right? Yeah. So our base is not base 10. This time we need to use 2 as the base number. Yeah. Then the standard representation, your bits number, right? So these little b's, that's your bits number 0 or 1. 2 cases. 2 possible numbers for the bits numbers. Yeah. All right. Here. Write this representation. Yeah. So this representation appears in your discrete math. Yeah. Discrete math, you have one chapter talking about, binary system. Yeah. All right. Then our B sub s, that's the most significant bit. The most significant bit should not be 0. Yeah. Otherwise, we remove it, right? We do not need to write that term. If it's a 0, so we go to the next B sub s1, s minus 1. Yeah. So we can assume this B sub s must be this 1 number. Most significant bit. Yeah. All right. Yeah. So then we can do the counting here. Yeah. So we do the counting. Yeah. Then the number of bits should be s plus 1. Yeah. Can you see why the number of bits should be s plus 1? In this representation, you have s plus 1 coefficients. Yeah. Because here we can use that. Because here you count the b coefficients directly. Yeah. The first coefficient, the subscript 0. Second coefficient, subscript 1. Next 2, and so on. The last one is s. So you count the number from 0 through s. It's s minus 1. Yeah. All right. So the answer is s minus 1, but you cannot use this as your final formula. You cannot use this s minus 1 as the final formula. The reason is our goal, we need to write the answer in terms of this n. in terms of this n. Yeah. Or you need to write S in terms of n. Okay? Write S in terms of n. Yeah. We don't want to see S in our formula, in our final formula. We want to see some function related to n function. Not the S function, n function. Yeah. So we need another step to get an n function here. Okay? All right. Yeah. So our next question, how to represent S in terms of n. Okay? How to represent S in terms of n. Okay? All right. Yeah. So we need to explore the relationship between S and n. All right? Yeah. So next, our second half, we need to derive the relationship between S and n. Yeah. So the question, how do we establish that relationship here? Yeah. Because all we know is this formula. All we know is this formula. Yeah. So now we need to apply this formula to establish relationship. So the left-hand side, we only have n at the left-hand side. Right-hand side, we have S. But how do we make the relationship much simpler? Yeah. So this relationship too complicated. We want to see a much simpler relationship. Yeah. In a more straightforward relationship. Yeah. All right. Here, the insight. Yeah. Here we need to do the transformation on the original formula. Transformation. Okay? All right. Here, the transformation, you need to take advantage of the special property of the structure. Take advantage of that special property. Okay, all right. The property, there is the base 2 property here. Base 2 property. Okay, all right. Yeah, so what kind of special operation related to base 2 is useful here? Yeah. All right. Then, so here the property is you need to do division by 2 operation. Division operation. Division by 2 operation, then you can do the transformation. You get an equivalent formula, but the form is different. The form is different. Okay? All right. So when you do division by 2, the left-hand side, you need to use the floor function because you want to get an integer, right? So here, we do division by 2, and we do integer division by 2 operation. Here, the operation we do is integer division by 2. So the both sides integers, division by 2. So we drop the remainder. We drop the remainder. Yeah. The remainder, only this B0 term contributes to the remainder, right? B0 term. Other terms, no remainder, right? Other terms, when you do division by 2, no remainder. Remainder is 0. Yeah. All right. But the B term, you may have some non-zero remainder, but we drop it, right? We drop it. When we do division by 2 operation, we drop it. That's why you see D0 is gone. Yeah. The D0 is gone, but all the other B's remain, and you reduce the corresponding power of 2, reduce its exponent number by 1. Yeah. Each exponent number of power of 2 is you reduce by 1 because division by 2. So you reduce it by 1. Yeah. So you get this formula. Okay. All right. So this formula, can you from this formula transformation, can you get something interesting? Yeah, from this formula transformation, you try to find some valuable information. Some valuable information. Okay? Yeah. First, from the left-hand side, you do size reduction. You reduce the size approximately by 2. Yeah. Approximately. Floor function. Yeah. Approximately by 2. The right-hand side, how much reduction do you get right-hand side? When you count the number of bits, how many bits fewer? When you compare number of bits in these two equations. Reduction, the number reduction. How much is the number reduction? 1, yeah, because you drop B0, so 1 reduction. So the right-hand side, 1 reduction. The left-hand side, half reduction. The problem size, half reduction. Yeah. That's the main property. Okay, that's the main property. That's our observation. Yeah. All right. We move the least significant bit. Yeah. Only 1 bit. We remove it, but least. So the number of bits reduced by 1. Yeah. The problem size is reduced by half. All right. Now we want to establish a new relationship. Recurrence relation. Size reduced by half, but the value number reduced by 1. Yeah. Value number reduced by 1. So let's introduce a new function. So here, yeah, the binary number, yeah, yeah, recursion, yeah. So here we define a new function. Okay, this new function give us the number of bits for n number, yeah, for n number. Then we have this recurrence relation. All right. So this function equals recursive function call, but at approximately half size. Half size. We use that value, okay, whatever it is. But you need to make up the difference part. The difference part is 1. Okay? So you derive this recurrence relation. Okay? So this is recurrence relation. You derive it. Okay? All right. Our next question, we need to solve it. We need to solve this recurrence relation. Yeah. All right. Yeah. So here we need, yeah, but we need a base case, right? Yeah. Base case. Yeah. When n equals 1, you use 1 bit. N equals 1, you use 1 bit. Okay. All right. Yeah. All right. Next, let us solve this recurrence relation. Yeah. All right. Yeah. And the division by 2, we can use the left shift operation. Yeah. So in our programming language, we have a special operation, shift to the left to the right. Right? Yeah. That operation, so you will see much faster than division. We know division is very slow, but shift operation is extremely fast. So that's why people create a new operation, shift operation, in programming languages. Yeah. So here we use the shift operation. So we can do much faster. Shift the decimal point or shift the binary point left to right. Yeah. That's extremely fast. Yeah. All right. Yeah, faster, even faster than addition. We know addition is pretty fast. Yeah. Addition is pretty fast, but much slower than multiplication. Remember, in our polynomial, that topic, I give you that ratio, 10-to-1 ratio, right? So the multiplication versus addition, that is 10-to-1 ratio. That difference, all right? So that division, so here let me give you the idea. Division versus addition, that's about 40-to-1 ratio. Very slow. Yeah. So that's why when we do division by 2, we know 2 is the base number. Division by 2, you just shift the decimal, binary point. Then you do not need to. You need because it's faster than addition. Addition is 1, right? So that shift even faster than 1. 1 unit of time. Okay? Yeah. Then the other way, 40. Division 40. Okay? Yeah. So now you can see why people use shift operations. Yeah. All right. Yeah. Then, So here, we want to calculate, solve. But at the same time, when we solve this recurrence, at the same time, we can consider the number of additions we use when we find the answer. Yeah, we need to do addition, right? Yeah. When we do calculation, we need to do addition. Yeah. So we create a new function. We call, new function a function. Represent a number of additions. Yeah. All right. Then the recurrence relation about this a function. Yeah. Yeah. When we calculate number of additions for n, yeah, because we need to work on the half size first, then plus one more addition, right? You plus one more addition. Yeah. Then for the base case, yeah, when n equals 0, we make a number of additions 1, okay? Yeah, because we do 0 plus 1 addition. Yeah, although it's unnecessary but convenient, right? Because in this way, this addition version same as the, original, that version. Yeah, yeah, same version. So same recurrence relation. Yeah. Now I want to show you how to solve this recurrence relation. Yeah. All right. To solve it here, I want to use this example to show you some more problem solving strategies and thinking. Yeah. When we solve problem like this. Yeah. Yeah. First, yeah, the problem. Yeah. First, recall some strategy we used before. Yeah. All right. This time, that strategy. Work on the simplest case first, that strategy. So what is the simplest case? Here. We need to, yeah, the cases. So here we do not modify the original problem. We still solve the same problem, but we want to work on the simplest case. Yeah. So here, what's the simplest case? All right. Here, when you look at this equation, which part you feel hard for you? Yeah. When you work on all the terms, which term do you feel hard to work on? Any particular part you feel a little hard to work? Yeah. How about this flow function? Is that flow function make it hard to work? Right? Yeah, because flow function, we feel hard to control. Sometimes we need to do truncation. Sometimes we do not need to do truncation, right? Yeah. When n is even, no truncation. But when n is odd, we need to truncate something. Yeah. But let's make the situation more complex, right? Yeah. So because in problem solving, we can make our assumption to make the situation easier for us. Yeah. So what kind of assumption you want to make your life easier? Yes. Just do it. Yeah. Yeah. If people ask you, how can you make that assumption? No. You can respond like this. We just work on the simplest case first, right? For the general case, after we solve the simplest case, then we can work on the general case. Yeah. So it's okay. Yeah. So you can make assumption. When n is even, then the flow function is gone. Okay? Yeah. So think about that. All right. So let's do it. Yeah. The flow function. Yeah. So first, we try to eliminate the flow function, because it increases the complexity of the problem. Yeah. All right. Yeah. Yeah. So the even case, yeah, simpler. Yeah. So we like the even case better. Yeah. So we make that assumption. n is even. Yeah. When n is even, yeah, so here we can remove. Yeah. All right, but after you remove floor function in the first equation, when you do the next recursion, yeah, because you need to go to the next level, right? Yeah. After you reduce problem, you need to go to another round recursion. But then in the next round recursion, the floor function of left-hand side you can remove because n even. But the floor function of the right-hand side you cannot remove, right? Because divided by 4, you may have some, non-integer part. Yeah. So now you have another chance to make your assumption, to remove that floor function. Another chance. Yes. Just make it. Assume this time n is a multiple of 4. Then next round, you have trouble again. Do you want to make another round assumption? Yes. Keep going like that. Yeah. It looks like you make too much, assumption. Yeah. But how about we do once for all? Let's make one assumption for all. Do once for all. How do you do to make one assumption for all, covering all the floor functions? Let n be power of 2. How about that? Yeah, we assume that n takes power of 2. Then all floor functions gone. Okay? Yeah. Yeah. So we are allowed to do that. Yeah, because our strategy, we work on the simplest case first. We treat that as the simplest case. Yeah, power of 2 case, that's the simplest case. Right. All right. Yeah. So now we assume n is power of 2. Okay? Yeah. Because this time all floor functions are gone. Okay? All right. Then k is log base 2 of n. Okay? Yeah. Relationship. Because at the end, we need to go back to n formula, not the k formula, right? N formula. Yeah. All right. New recurrence relation. Yeah. So this time, a of 2 to the k equals a of 2 to the k minus 1 plus 1. You can see all floor functions are gone. Okay? Yeah. So that's very nice. All floor functions are gone. Okay? All right. Next, now we need to find a solution for this capital A function. Yeah. All right. Yeah. Let's do the work. Yeah. All right. The next one, another recursion. Yeah. So second equation. And the next equation, yeah. So we keep writing all these recurrence equations. Yeah, all these, yeah, so that's all the possible, yeah, we write, yeah. Then, if you add up all these equations, both sides, add up all these equations, you can cross out the terms from both sides in this way, right? Yeah, yeah. So cancel out, yeah, like that, yeah. Then, what you get is 2 to the k equals, yeah, so here. How many equations? Can you count how many equations do you have? Do you have some special way to help you make that counting? We learned that special method before. Yeah, not invariance. This time, counting by reference. Yeah. This time we apply this counting by reference. Can you find some appropriate reference here? Yeah. All right. This equation, can we use the superscript, this 0 as its reference? All right. So this equation we use, it's k minus 1 as the reference. this one k minus 2 as the reference. Okay? Consecutive integers from 0, 1, 2, dot, 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 k minus 2, k minus 1. These are the reference numbers. When you count the number equations, is it the same? You just count the number of consecutive integers here, right? Yeah, that's the counting by reference method. How many integers here? From 0 through k minus 1. Don't plus 1, yeah. Because this k minus 1 plus 1, okay?
Oh, so the end is k minus 1.
Yeah.
Oh, okay,
Yeah, yeah. So that's why we have k. We have k, okay? We have k. But why this 1? Because this 1 is the a value, okay? Because a of 2 to the 0, that's a of 1 plus k, okay? A of 1, that's 1. A of 1, that's 1. That's why we have k plus 1. All right. Then, conclusion. After that, we need to write the final formula, the conclusion. Yeah. First, yeah, we need to go back to n. We need to go back to n, all right? Yeah. So the result, a of n equals 1 plus log base 2 of n. Yeah. A of n, because that 2 to the k, that is just the n. So we replace 2 to the k by n. Then 1 plus k, replace k by log base 2 of n. Okay? So this is our final formula. Okay? Yeah. So this is our final formula. Yeah. Yeah. All right. But after you get a final formula, then don't forget we make that big assumption. So this formula is true under our big assumption, power of 2 assumption. So if it's not power of 2, then you cannot use this formula. Only when n takes power of 2, then you can take that formula. Yeah. But our goal is not this. Our goal, we want to find a formula for any n, not just power of 2. For the general n, not power of 2. So we need one more important step to go. Yeah. The question, how to make that step? Yeah. Yeah. All right. So, looks a lot of work we need to do. Yeah. Yeah. So that one. All right. Remember, I talked about another strategy before. So here. Several strategies. We keep using those strategies. Another strategy I called guess and verify strategy. Still remember? We make a guess first. In our string matching problem, we applied one effective strategy in problem solving. We called guess and verify. You need to make a guess first. After you make that guess, then you verify it. Yeah. So in problem solving, that strategy very effective. Here we need to use that strategy. Now, we want to go from the power of 2n to the general n. Oh, yeah, so I run out of time. So I need to close it in 2 minutes. Yeah. All right, yeah. All right, make that guess. All right. For the general case, yeah. The base of our guess is this formula. Yeah. Because when we make a guess, we cannot make a baseless guess, right? Yeah, random, arbitrary guess, that's ridiculous. Yeah. But we have a solid base. This is a solid base. So when we make a guess based on this information, very useful information, then based on this information, we can modify this formula to get our guess. Yeah. To make that guess, yeah, because here, first, this log base 2 function is not necessarily integer in general, right? Log base 2 of arbitrary n. Most of the time, it's not integer. Yeah. So if it's not integer, we want to convert it to integer. Yeah. The question is, how do we convert a non-integer expression to some integer expression in a relatively easy way? Yes. Floor function is one option, ceiling function. How about ceiling function? Floor function or ceiling function? So we have two options, floor function or ceiling function. Yeah, you need to consider. Okay, all right. Let me leave that to the next time. Next time we try to see why one function is correct, but the other function is incorrect. Yeah. All right, that's it. See you Wednesday.